A sudden crackle from the void defies all known physics. This is the startling reality for astronomers listening to the cosmos, and it leads us to one of modern astronomy's greatest enigmas. We are talking about 20 unexplained signals from deep space that baffle scientists. These are not science fiction. They are cosmic whispers, from mysterious repeating patterns to powerful one-time bursts that challenge everything we think we know. By staying until the end, you will gain a front-row seat to the scientific detective work unraveling these mysteries and understand why each signal could rewrite our cosmic rulebook. What causes a blast of energy that outshines the sun in a millisecond? Could a perfectly timed pulse ever be a message? The answers are waiting at the very edge of known science. What do you believe is the most likely explanation for these cosmic secrets? The universe broadcasts on a frequency our ears cannot hear. It sings a constant, chaotic radio symphony, a background hum of energy left over from the birth of everything. For decades, scientists have built enormous ears to listen. Giant parabolic dishes like the late Arecibo Observatory in Puerto Rico, or sprawling networks like the Very Large Array in New Mexico, act as cosmic hearing aids. They do not listen for sound but for radio waves, a form of light invisible to our eyes that travels effortlessly across the gulfs between stars. These telescopes collect the faint whispers of the cosmos, the natural radio emissions from swirling galaxies, dying stars, and spinning neutron stars called pulsars, which tick with metronomic regularity. This is the established orchestra of deep space, a cacophony scientists have learned to identify and understand. Against this backdrop of natural noise, a dedicated group of researchers listens for something else, a single wrong note in the symphony. This is the search for extraterrestrial intelligence, known as SETI, a scientific endeavor that scans the radio dial for any pattern that seems engineered, any signal that carries the signature of a mind. For every potential blip, the process is ruthlessly skeptical. Is it a passing satellite, a microwave oven in the observatory kitchen, or a glitch in the instrument itself? To be considered truly unexplained, a signal must survive a gauntlet of tests, ruling out every known source, both human and cosmic. That is why the rare signals that remain, the ones that baffle the brightest minds, are not just curiosities. They are profound anomalies, cosmic puzzles that challenge our very understanding of what is possible out there in the dark. That cosmic symphony was playing as usual on a quiet August night in 1977. At the Big Ear Radio Telescope in Delaware, Ohio, data was printing out line by line on continuous green and white paper. An astronomer named Jerry Amon, part of the Ohio State University SETI project, was volunteering his time to review the latest data the next day. His task was to scan these long columns of letters and numbers, a code representing signal strength, looking for anything unusual. On August 16th, his eyes stopped on one line. The sequence showed a signal so powerful it maxed out the telescope's scale. In the margin, Amon circled the alphanumeric code, 6 letters and numbers that spelled out an intensity never before seen. Beside it, he wrote a single word in red pen. Wow, that 72-second burst of radio waves detected at a frequency of 1,420 MHz was not just strong. It was precise. It appeared in a very narrow band of the radio spectrum, the kind of clean, focused signal you would expect from a transmitter, not a natural cosmic event. Even more intriguing, that frequency is a cosmic landmark. It is the resonant frequency of neutral hydrogen, the most common element in the universe. Any civilization with a basic understanding of astronomy might choose it as a logical channel for a beacon. a universal hello on a frequency everyone would think to monitor. The signal rose and fell in a perfect curve over 72 seconds, exactly matching what you would see as the Earth rotation swept the stationary telescope's field of view over a fixed point in space. It came from the direction of the constellation Sagittarius toward the center of our galaxy, and then it was gone. For 45 years, astronomers have pointed every available instrument toward that patch of sky. They have ruled out passing aircraft, reflected signals from satellites or space debris, and even distant comets that happened to be in the area. The WOW signal was a one-time event, a shout into the void that has never been answered or repeated. It stands alone as the most famous, the most perfectly formed unexplained signal in history. It is the ghost in the machine of SETI, a persistent reminder that for one brief moment, the universe seemed to speak with a clarity we still cannot explain. If it was a natural phenomenon, it is one our physics has yet to describe. If it was something else, the implications are profound. It remains the tantalizing standard against which all other mysteries are measured. A single, brilliant question mark written in red ink on a faded computer printout. The WOW signal was a perfect, singular question, but the cosmos soon began asking far more violent ones. In 2007, an astronomer named Duncan Lorimer was reviewing archived data from a radio telescope in Australia, searching for new pulsars. Buried in observations from 2001, he found something that did not fit any known pattern. It was a spike of radio energy so brief it lasted just 5 milliseconds, a flicker shorter than the blink of an eye. Yet in that instant, it released more energy than our sun emits over 80 days. He had discovered the first documented fast radio burst, an event so powerful and so fleeting it defied all logic. Since that moment of recognition in old data, hundreds more of these bursts have been detected, arriving from every direction in the sky. Each one is a cosmic flashbulb, popping off in the deep darkness of intergalactic space, billions of light years from Earth. The distances are staggering. To be visible across such gulfs, the source must be unleashing an almost unimaginable concentration of power. Imagine all the energy produced by every power plant on Earth for 1 million years, focused and released in the time it takes a camera shutter to click. That is the scale of violence we are talking about. The leading suspect in this cosmic mystery is a type of stellar corpse called a magnetar. These are neutron stars, the incredibly dense remains of a giant star's core after a supernova, but with a magnetic field trillions of times stronger than Earth. Think of a magnet so powerful it could erase a credit card from halfway across the solar system. Astronomers theorize that starquakes on the surfaces of these magnetars, or sudden rearrangements of their unimaginably strong magnetic fields, could crack like a whip, producing the titanic, fleeting radio flashes we see as FRBs. Some bursts even repeat, sending out multiple signals from the same patch of sky, which has allowed telescopes to pinpoint their home galaxies. Yet the sheer diversity of FRBs, with some repeating erratically and others firing just once, suggests we might be looking at more than one kind of cosmic engine. Other, more exotic ideas have been proposed, like collisions between ultra-dense objects or even the theoretical snap of cosmic strings, defects in the fabric of space-time itself. Each new detection is a clue, but the central puzzle remains. What natural process can possibly be so efficient, so devastatingly powerful, and so brief? Fast radio bursts are not just signals, they are cosmic emergencies, urgent telegrams from the most extreme environments in the universe, and we are only just beginning to translate their violent, millisecond language. The violence of a single fast radio burst is shocking, but its finality leaves scientists with only a single, fading snapshot. What if the universe decided to send a sequel? In a distant dwarf galaxy, 3 billion light-years from Earth, A source designated FRB 121102 did exactly that. This was not a one-time cosmic catastrophe. It was a repeater, sporadically firing off multiple bursts over years, shattering the early assumption that all FRBs were the death cries of celestial objects. Its very existence changed the game, proving that whatever engine powers these events could survive its own outburst and fire again. This repetition offered a priceless opportunity. For the first time, astronomers could point their most powerful telescopes, like the Very Large Array, at a known FRB location and wait. They were rewarded not just with more bursts, but with a precise cosmic address. They traced FRB 121102 back to a tiny, faint dwarf galaxy, a stellar environment quite different from our own Milky Way. This galaxy is actively forming new stars at a furious rate, a nursery for stellar violence. Further study revealed something even more peculiar. The bursts seemed to be coming from an incredibly turbulent region, possibly near the galaxy's central supermassive black hole or embedded within a dense, energetic nebula, a cloud of gas and dust swirling with magnetic fields. This unique environment is a key clue. The fact that the source persists in such a chaotic neighborhood strongly suggests it is a resilient object, something that can withstand repeated titanic releases of energy without being utterly destroyed. The leading candidate is a special kind of magnetar, one that is exceptionally young and active, perhaps still surrounded by the chaotic debris of its own violent birth. Each time its crust shifts or its magnetic field lines snap and reconnect, it could unleash another millisecond flash powerful enough to cross 3 billion light-years. The discovery of this repeater did more than provide a target. It forced a fundamental rethink. It told astronomers that the universe has at least two classes of FRB sources, the one-off cataclysms and the persistent repeaters. This opened the door to a universe filled with different kinds of cosmic radio transmitters, each with its own story, its own reason for shouting into the dark. Sometimes the most revolutionary discoveries are not seen, but heard in the data years later. The story of the Lorimer burst begins not with a flash in a telescope eyepiece, but with a patient sifting through old observations. Astronomer Duncan Lorimer and his student were analyzing archived data from the Parkes radio telescope in Australia, a massive dish often called the Dish, searching for new pulsars. Their routine work in 2007 focused on recordings from 6 years prior, a magnetic tape holding the whispers of the sky from 2001. As their software scanned, it flagged a single point of data so extraordinary the algorithm nearly rejected it as an error. It was a burst of radio waves lasting just 5 milliseconds, but its profile was unlike any known pulsar or piece of human-made interference. It was a cosmic spike of pure energy, a shout so loud and so brief it seemed impossible. The initial reaction within the scientific community was deep skepticism. A signal that powerful, coming from far beyond our galaxy, contradicted established understanding of what was physically possible. Many astronomers reasonably suspected it was a local glitch, a burst of terrestrial noise perhaps from a passing satellite or even a microwave oven in the observatory break room, a known culprit that had polluted data before. The idea that such an immense release of energy could occur in a fraction of a blink and from so far away was almost heretical, yet the data was stubborn. The signal's characteristics held clues to its extragalactic origin. A key signature was its dispersion, a slight smearing of the burst across different radio frequencies. This happens because radio waves travel through the sparse gas between galaxies, which slows lower frequencies very slightly more than higher ones. By measuring this smear, Lorimer could estimate how much material the signal had traveled through, and the answer pointed to a journey of billions of light-years. This was the proof. The Lorimer burst was not from our neighborhood. It was a telegram from a distant universe, and its discovery paper cautiously introduced the world to a phenomenon they called a fast radio burst. It taught astronomers a vital lesson. To find the extraordinary, they had to first believe it was possible, and then learn to recognize its unique fingerprint in a sea of noise. This single, anomalous point on a graph became the cornerstone, revolutionizing how we listen to the cosmos by proving that the universe holds millisecond secrets of staggering power, waiting for anyone patient enough to look back through the static. The Lorimer burst was a solitary, brilliant flash in the archival dark, but to truly understand a phenomenon, you need more than a single specimen, you need a population. Enter a revolutionary instrument that turned a trickle of mysteries into a flood of data. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, is not a traditional dish. It resembles 4 massive half-pipes, each the length of a football field, sitting in a radio-quiet valley in British Columbia. This stationary array has no moving parts. Instead of steering to point at one part of the sky, its design allows it to see the entire northern sky every single day as the Earth rotates. It is a cosmic surveillance camera, constantly recording the radio heavens. Originally built to map the faint radio glow of cosmic hydrogen from the distant universe, its designers soon realized it was perfectly tuned to catch the fleeting millisecond flashes of fast radio bursts. Since it began full operations, CHIME has revolutionized the field, detecting hundreds of FRBs, including dozens of new repeating sources. This is not just an increase in numbers, it is a fundamental shift in perspective. Before CHIME, each FRB was a rare treasure, a singular event to be pored over. Now, astronomers have a catalogue. They can study statistics, patterns, and demographics. They can ask new questions. Are repeaters fundamentally different from one-off bursts? Do they come from different types of galaxies or cosmic environments? The sheer volume of detections tells us these events are not rare cosmic flukes. They are commonplace. Current estimates suggest a fast radio burst goes off somewhere in the observable universe roughly every single second. This transforms them from mere curiosities into a powerful new tool. Each burst is more than a flash, it is a probe. As the radio waves travel billions of light years to reach us, they pass through the diffuse clouds of gas and magnetic fields that make up the cosmic web, the vast, invisible scaffolding of the universe. This material leaves a subtle fingerprint on the signal, a smear of dispersion that CHIME measures with incredible precision. By analyzing thousands of these fingerprints, scientists are beginning to do something extraordinary. They are using FRBs to weigh the missing matter of the universe, to map the invisible threads between galaxies. What started as a search for mysterious explosions has given us a new way to see the darkness itself, painting a picture of the cosmos with bursts of enigmatic light. While powerful telescopes like CHIME scan the heavens, another kind of search was happening on a far more personal scale. It relied not on a single giant dish, but on the combined power of millions of ordinary computers. The SETI at Home project, launched in 1999, invited anyone with an internet connection to join the hunt. By running a screensaver program, volunteers donated their computers' idle processing power to analyze mountains of radio telescope data, searching for the subtle signature of an artificial signal. It was a vast, distributed electronic ear, listening with the collective curiosity of humanity. In 2004, this global network flagged a candidate that would become known as SETI-02+14a. The signal originated from a seemingly empty point of sky between the constellations Pisces and Aries. It was faint, but it appeared 3 separate times, always hovering around 1420 MHz. That frequency is a cosmic landmark, the natural emission line of neutral hydrogen, the most common element in the universe. Scientists have long theorized that any technological civilization might recognize this as a logical, universal channel for a beacon, a quiet place in the radio spectrum where one might whisper across the stars. The fact that SHB 02 plus 14 appeared near this hallowed frequency, and more than once, was enough to spark intense excitement. Here was a potential signal that seemed to be doing what a beacon should do, repeating from a fixed point in the cosmos. The discovery, made by a citizen scientist's computer, felt like a validation of the entire crowdsourced approach. It was a moment where the dream felt tantalizingly close. Yet science demands more than tantalizing clues, it demands verification. Major radio telescopes around the world were pointed at that precise coordinate, listening intently for a fourth repetition for confirmation. The silence that followed was profound. No trace of the signal was ever heard again by any professional instrument. The most likely explanation is a cruel but common one in radio astronomy, a combination of random noise and persistent radio frequency interference, perhaps from an earthly source, aligning by sheer chance to mimic a promising pattern. SHB 02 plus 14 stands not as a confirmed contact but as a powerful lesson. It exemplifies the monumental challenge of this search, the equivalent of identifying a single, specific whisper in a hurricane. For every potential signal that captures our imagination, there are countless mirages born of chaos and coincidence. Yet its legacy is not one of disappointment, but of democratic possibility. It proved that the search belongs to everyone, and that the next anomalous whisper could come from anywhere, even from a screensaver on a home computer, quietly sifting through the static of the universe. The search for whispers in the radio static is often driven by a much stranger visual discovery. In 2015, astronomers working with data from the Kepler Space Telescope, a planet hunter, identified a star with a light curve unlike any other. Designated KIC 8462852, but better known as Tabby star, this otherwise ordinary sun displayed bizarre, irregular dimming events. It would fade by enormous amounts, up to 22%, in ways that no known planet, not even a Jupiter-sized world, could explain. The dips were asymmetric, chaotic, and deep, suggesting something vast and oddly shaped was periodically blocking its light. In the absence of a clear natural explanation, a provocative hypothesis emerged. Could the dimming be caused by a vast swarm of artificial structures, a so-called Dyson swarm, built by an advanced civilization to capture the star's energy? This was the alien megastructure idea, and while most scientists considered it highly unlikely, it was a testable proposition. If a civilization capable of such engineering existed there, it might also produce other detectable signs of technology, like radio transmissions. This optical mystery immediately triggered a radio quest. Teams pointed one of the world's most sensitive instruments, the Green Bank Telescope, toward Tabby star, listening across a wide range of frequencies for any hint of a technosignature, a signal bearing the mark of intelligence. They searched for both narrowband signals like a focused beacon and broader signs of leakage, the radio equivalent of the hum from a vast civilization's machinery. The result was profound silence. No unusual radio emissions were found. This non-detection, while perhaps disappointing to some, was a crucial piece of scientific evidence. It helped rule out one of the most exotic explanations, steering the investigation back toward natural, if still mysterious, astrophysical causes. The leading theories now involve swarms of comets, clouds of dust from a shattered planet, or complex interstellar material passing in front of the star. The case of Tabby star is a perfect lesson in how modern astronomy works. An anomaly in one wavelength, like starlight, immediately prompts a forensic investigation across the entire electromagnetic spectrum. Sometimes what you do not hear is just as important as what you do. The absence of a radio signal tightened the constraints on the mystery, proving that the universe's strangest puzzles often require us to listen closely, even when we are looking at something else entirely. The profound silence from Tabby's star underscored a universal truth in this search, that hope is often followed by rigorous, sobering scrutiny. This cycle of excitement and analysis reached a fever pitch in late 2020, with a signal that seemed almost too perfect to be true. The Breakthrough Listen project, one of the most comprehensive scientific searches for extraterrestrial intelligence, was using the Parkes radio telescope in Australia to observe our closest stellar neighbor, Proxima Centauri. This red dwarf star, a mere 4.2 light-years away, is known to host at least one Earth-sized planet within its habitable zone, a world where liquid water could theoretically exist. Amid the terabytes of data, researchers found a needle in the cosmic haystack, a signal they named BLC1. It was a narrowband radio emission, a sharp, pure tone concentrated on a single frequency, exactly the type of clean, engineered signature a technological civilization might produce. Even more compelling, the signal exhibited a frequency drift, a slight shift in pitch over time. This drift perfectly matched what you would expect if the source was on a planet orbiting its star, the motion causing a Doppler shift similar to the changing pitch of a passing ambulance siren. For a moment, it appeared science had struck gold, a potential signal from an Earth-like world right next door. The news sent a legitimate thrill through the scientific community and the public imagination. Here was a candidate that ticked every box on the initial checklist, originating from the most tantalizing location imaginable. The analysis that followed, however, was a masterclass in scientific skepticism. A dedicated team spent months subjecting BLC1 to every conceivable test. They examined it for signs of modulation, for hidden patterns within the tone. They searched for other signals at different frequencies that might accompany it, as human technology often produces. Most critically, they looked for it again. Despite extensive follow-up observations with Parkes and other telescopes, BLC1 never reappeared. The final conclusion was a letdown, but a definitive one. The signal was almost certainly human-made radio frequency interference. Its characteristics pointed to a source like a poorly shielded electronic device on Earth's surface, or perhaps a satellite in a highly elliptical orbit that briefly passed through the telescope's field of view. The drift, which seemed so promising, was likely caused by the relative motion between that human technology and the moving telescope on Earth. This episode is not a story of failure, but a crucial revelation of scale. It highlights the extreme, almost paradoxical difficulty modern SETI faces. Our planet is now enveloped in a dense, radiating shell of our own making, a constant chatter of satellites, mobile phones, radar, and everyday electronics. Distinguishing a genuine whisper from another star from this omnipresent human cacophony is like trying to hear a single unique voice in a packed, roaring stadium. Every promising signal must first prove it is not just an echo of ourselves, a reflection of our own technological adolescence bouncing back at us from the silent stars. The quest for cosmic signals is a constant battle against our own noisy planet. At the legendary Parkes radio telescope in Australia, astronomers for years were puzzled by a series of peculiar bursts they called Perytons. These signals had the classic hallmark of something from deep space, a telltale smearing across frequencies caused by dispersion through interstellar gas. They looked for all the world like the elusive fast radio bursts scientists were desperate to find. Yet these Perytons had a curious consistency. They only ever appeared during daytime observations at Parkes. This was the first major clue that their origin was not cosmic but decidedly local. The mystery deepened into a significant nuisance as these false alarms muddied the waters of genuine FRB research, casting doubt on every new detection. How could scientists trust a signal from a distant galaxy when similar-looking interference was popping up right outside the control room? The solution arrived not from a deeper analysis of star charts, but from a moment of everyday human impatience. Researchers eventually discovered the source, the microwave oven in the observatory staff kitchen. When an observatory staff member heated their lunch and then opened the oven door before the timer had fully finished, the safety mechanism that stops the microwave's magnetron created a brief, powerful burst of radio waves. This pulse would escape the kitchen, travel across the observatory grounds, and be picked up by the gigantic, sensitive ear of the park's dish. The telescope, designed to catch whispers from billions of light years away, was also perfectly tuned to hear the click of a door hinge 50 meters away. This revelation was met with a mix of humor and profound relief. It became a legendary cautionary tale in astronomy, underscoring a fundamental truth: before you can listen to the universe, you must learn to silence the Earth. The Peryton episode highlights the rigorous, often mundane detective work that underpins every cosmic discovery. It reminds us that the path to extraordinary truths is paved with the patient elimination of ordinary explanations, even those that smell like leftover pizza. Our own galaxy's core holds a secret that pulses with a strange, patient rhythm. While telescopes strain to hear whispers from billions of light years away, a much closer anomaly was broadcasting from our own cosmic neighborhood, a mere 28,000 light years from Earth in the bustling center of the Milky Way. In the early 2000s, a team analyzing data from the Very Large Array Radio Telescope stumbled upon a source that defied simple classification. Designated GCRTJ 1745-3009, it became known as the Galactic Center Radio Transient. Its behavior was hypnotically odd. Roughly every 77 minutes, it would erupt in a burst of bright, coherent radio waves, a clean, powerful signal lasting about 10 minutes before fading back into the background noise of the galactic center. This was not the rapid, millisecond click of a pulsar, nor was it the violent, one-off blast of a distant fast radio burst. This was something in between, a slow, repeating heartbeat in the radio band with a personality all its own. The strangeness lies in the details. A typical pulsar is a rapidly spinning neutron star, beaming radiation like a lighthouse with metronomic precision, often hundreds of times per second. The pulses from GCRTJ 1745-3009 were far too long and too irregular to fit that model. Its 77-minute cycle is leisurely by cosmic standards, and the bursts themselves showed subtle variations in shape and strength from one cycle to the next. This pointed to a source that was not simply a spinning corpse, but something more dynamic, perhaps an object whose magnetic environment or energy release process was changing in real time. For over a decade after its initial detection, the source went quiet, refusing to repeat its performance for follow-up observations, deepening the mystery. Then, in 2021, it suddenly flared back to life, detected again by the Meerkat Array in South Africa, confirming it was not a one-time glitch but a persistent, if elusive, phenomenon. So what could it be? The leading theories focus on failed stars and hidden dances. One compelling idea is that it is a highly magnetized, solitary brown dwarf. A brown dwarf is an object too massive to be a planet, but not massive enough to ignite sustained fusion in its core, often called a failed star. If such an object possessed a magnetic field thousands of times stronger than Jupiter's, interactions within its atmosphere or with a surrounding disk of material could generate the periodic, coherent radio outbursts we see. Another possibility is a novel type of interacting binary system, perhaps a brown dwarf or a low-mass star in a tight orbit with a white dwarf or another dense object. Their gravitational and magnetic interplay could create a periodic build-up and release of energy, like a cosmic capacitor discharging every 77 minutes. What makes this mystery so valuable is its location. Unlike the extragalactic fast radio bursts whose distances make detailed study challenging, this transient is in our own galaxy. It is a nearby laboratory for studying a completely different class of non-thermal radio burst, a reminder that we do not need to look to the edge of the observable universe to find profound enigmas. Sometimes the most puzzling signals are coming from our own galactic heart, ticking away with a slow, inscrutable patience, waiting for us to understand their language. The slow, patient heartbeat from our galaxy's center is a mystery we can study for centuries. But sometimes the universe seems to shout from a place that feels almost familiar, a star that could be a cousin to our own sun. In late August of 2016, astronomers at the Ratan 600 radio telescope in Russia detected a powerful, unusual signal. It was a strong, narrowband burst at 11 GHz, a frequency used for satellite communications and radar, and it appeared to originate from the direction of a star called HD 164595. This was not a random point of darkness. This star, located about 95 light-years away in the constellation Hercules, is remarkably Sun-like. It is slightly older and a bit brighter than our own star, but of the same spectral type, and we know it hosts at least one Neptune-sized planet. For a brief, electrifying moment, all the pieces seemed to align, a strong signal from a Sun-like star with a known planetary system. The news, when it quietly reached the SETI community, triggered an immediate and global response. This is where modern astronomy's rapid response network snapped into action. Within hours of the alert, some of the world's most powerful radio ears, including the Allen Telescope Array in California and the Green Bank Telescope in West Virginia, were pointed at HD 164595. They listened intently across a wide range of frequencies, searching for a repeat of the signal or any other anomalous emission. This coordinated effort is the scientific equivalent of a full court press, designed to verify or debunk a potential discovery as quickly as possible. The result, however, was a unanimous and definitive silence. No other telescope on Earth detected anything unusual from that star. The swift follow-up allowed scientists to triangulate the truth. The signal's characteristics and its failure to appear anywhere else pointed overwhelmingly to a terrestrial origin. The most likely culprit was a military or civilian satellite transmission, a piece of human technology passing through the Ratan telescope's field of view. Its signal reflected or picked up in a way that mimicked a cosmic source. The excitement around HD 164595 lasted only a few days, but its legacy is a powerful lesson in scientific efficiency. It demonstrated a protocol that works. The rapid sharing of data and the instant worldwide collaboration turned what could have been a years-long mystery into a case closed in a matter of days. While the outcome dashed the fleeting hope of contact, it proved something equally important: our ability to work together as a global scientific community to separate the profound wonders of the cosmos from the mundane clutter of our own orbiting machinery. The stars remain silent not for a lack of listening, but because we are now sophisticated enough to recognize our own reflection in the void. Sometimes the most promising signal is not a mystery at all, but the key that unlocks an entirely new chapter of astronomy. In the crisp autumn of 1967, a young graduate student named Jocelyn Bell Burnell was reviewing data from a newly built radio telescope in Cambridge, England. The telescope was designed to study the twinkling of distant quasars, but Bell Burnell noticed something odd in the long paper charts, a bit of what she called scruff, a small, persistent signal that did not look like cosmic interference or a known source. It was a series of pulses perfectly spaced 1.33 seconds apart, ticking with a regularity more precise than any human clock. This was not a whisper or a burst, it was a metronomic beat, a steady rhythm emanating from deep space. The signal was so unnervingly regular, so artificial in its perfection, that the small research team humorously labeled it LGM-1 for Little Green Men. For a few thrilling and anxious weeks, they genuinely entertained the possibility that they had detected a beacon, a cosmic lighthouse built by an intelligence trying to make contact. The idea was not taken lightly. It was a profound and secret burden. They quietly checked and rechecked their equipment, ruling out terrestrial sources, satellites, or any other human-made origin. The pulse was real, and it was coming from the cosmos. The moment of revelation came not from contact with another civilization, but from a deeper understanding of physics. Bell Burnell soon discovered a second, similar pulsing source in a different part of the sky. The chance of two separate civilizations choosing to broadcast on nearly identical rhythms was vanishingly small. The truth was far more extraordinary than little green men. They had discovered the first pulsar, the rapidly spinning, ultra-dense core of a massive star that had died in a supernova explosion. This neutron star, only about 12 miles across but containing more mass than our Sun, was spinning over 600 times per minute, its intense magnetic field funneling beams of radiation that swept past Earth like a lighthouse beam with every rotation. That precise 1.33-second tick was the spin rate of a stellar corpse. The discovery earned the project's supervisor a Nobel Prize, a controversial omission of Bell Burnell herself that the scientific community now widely recognizes. Yet the legacy of LGM-1 is not one of disappointment but of cosmic revolution. This solved mystery did not close a door, it blew it wide open. The identification of pulsars gave astronomers a powerful new tool, a natural cosmic clock of incredible stability. These ticking beacons have since been used to test Einstein's theory of gravity, to map the structure of our galaxy, and even to aid in the first indirect detection of gravitational waves. It stands as a beautiful testament that the greatest discoveries often come from the signals we cannot immediately explain, not because they are messages, but because they are signposts pointing toward entirely new realms of reality, waiting for a curious mind to decipher their true, magnificent nature. The discovery of pulsars taught us to listen for cosmic clocks, but some rhythms defy that simple ticking. Beyond the frantic millisecond flashes of fast radio bursts, the deep sky holds slower, more patient cadences that whisper of a different kind of order. Astronomers now occasionally detect unexplained repeating signals with mysterious periodicities, intervals that range from minutes to days, each cycle a metronome marking time for an engine we cannot see. One recently discovered source, for instance, emits a powerful radio burst on a remarkably consistent 16-day cycle. It remains active for a 4-day window, blasting out multiple signals, then falls completely silent for 12 days before starting the pattern all over again. This is not random chaos, it is a schedule, a cosmic appointment kept with eerie regularity. Analyzing these patterns is a meticulous science of elimination. The first question astronomers ask is about motion. Could this steady pulse be the signature of an orbit? Imagine a dense object like a neutron star circling a companion. If it has an active magnetic region that faces us only during a specific part of its long orbit, that could create a periodic flash, much like seeing the beam of a lighthouse only when it spins toward the shore. The 16-day period is particularly suggestive as it falls into the range of orbital timescales for binary systems. Another possibility is precession, a slow wobble in the spin axis of a highly magnetized star. As it wobbles over months or years, its beam of radiation might sweep across Earth's line of sight only during a specific phase of that wobble, creating a predictable on and off switch for the signal we receive. Yet when the math is done, the simplest explanations often fall short. The periods are sometimes too stable, or the signal's character too complex to fit neatly into our models of orbiting or wobbling stars. This consistency is the ultimate clue and the central puzzle. A strict periodicity points to a system of incredible stability, a cosmic mechanism that can regulate immense energy releases with the precision of a Swiss watch. But what natural engine, operating under the most extreme gravitational and magnetic stresses imaginable, can maintain such a perfect, long-term rhythm without breaking? It suggests a balance of forces we have not yet witnessed, perhaps in an object at the very edge of theoretical possibility, like a magnetar interacting with a debris disk in a delicate, sustained dance. Each repeating cycle is a heartbeat from the dark, a reminder that for all we have catalogued, the universe still holds systems that operate on timetables written in a physics we are only beginning to translate. The precise heartbeat of a repeating signal suggests a universe governed by clocks, but what if we are only listening to one channel? The search for cosmic intelligence is undergoing a quiet revolution, expanding its senses far beyond the familiar crackle of radio static. This broader hunt is for technosignatures, any detectable sign of past or present technology, and it forces us to ask a humbling question. What if an advanced civilization does not broadcast on frequencies we can easily hear, but instead leaves footprints in the light itself? Imagine scanning the heavens not for a message, but for the glow of their cities, the shadow of their engineering, or the flash of their own form of communication. This is not science fiction, it is the logical next step in a cosmic investigation. Projects like laser SETI are now scanning the sky with arrays of sensitive cameras, searching for brief, powerful pulses of optical or infrared light. The concept is straightforward. A civilization might use tightly focused laser beams for interstellar communication, far more efficient than broadcasting radio in all directions. Such a laser, even from many light years away, could appear as a star-like pinpoint that flashes for a nanosecond, a sudden, unnatural spike in the darkness. Finding it requires staring at vast patches of sky continuously, looking for that one impossible flicker. Other searchers look for signatures of vast energy use. The theoretical physicist Freeman Dyson once speculated that a truly advanced civilization might eventually enclose its star with a swarm of energy-collecting structures, a Dyson sphere. While a complete sphere is likely improbable, even a partial swarm would have a distinct infrared signature, radiating the waste heat of an entire civilization's industry. Telescopes like NAS, a wide-field infrared survey explorer, have scanned millions of stars for exactly this, an object that is unusually bright in the infrared but dim in visible light, a star that seems to be wearing a technological cloak. The search even extends to looking for unnatural substances in a planet's atmosphere. On Earth, our industrial age has filled the air with chemicals like chlorofluorocarbons and nitrogen dioxide, pollutants that would be detectable in our atmospheric spectrum from light years away. An alien astronomer might see those as a technosignature, the chemical marker of a world alive with industry. By broadening the search across the entire electromagnetic spectrum and into the realm of chemistry and physics, scientists are acknowledging a profound possibility. Our current bafflement at the lack of clear radio signals might simply reflect a limited perspective. We are searching for civilizations that communicate like a 21st century Earth, but a society a million years more advanced might use methods we have not yet dreamed of, leaving traces we are only just learning how to see. The silence, then, is not an answer. It is an invitation to look deeper in every wavelength for the fingerprints of a cosmic architect. The search for cosmic architects leads us back to a violent, natural sculptor, one whose power is almost beyond imagination. Among the most promising keys to unlocking many signal mysteries is not a distant intelligence, but a specific type of stellar corpse, the magnetar. To understand its power, picture a star much larger than our Sun. When such a star exhausts its fuel, it does not fade quietly. It explodes in a supernova, blasting its outer layers into space. What remains is the collapsed core, a neutron star. If you could take all the mass of our Sun and crush it into a sphere the size of a city, you would have something of this impossible density, a teaspoon of its material would weigh as much as a mountain. Now take that concept and turn the magnetism up to an almost inconceivable level. A magnetar is a neutron star born spinning furiously and endowed with a magnetic field 1,000 trillion times stronger than Earth's. This is not just a strong magnet, it is a fundamental force that warps the very nature of matter around it. If a magnetar were located halfway between Earth and the Moon, its magnetic field would be strong enough to erase every credit card on our planet. It exists in a state of unimaginable stress, its rigid crust of iron nuclei strained over a fluid interior, like a thin eggshell over a boiling sea. This constant titanic pressure is what makes magnetars such compelling suspects for cosmic radio bursts. Astronomers theorize that these stars experience starquakes. The crust, under unbearable strain, suddenly cracks and shifts, a seismic event on a stellar scale. This crustal movement sends powerful vibrations through the star's intense magnetic field, which is frozen into the crust like lines in a colossal fingerprint. The snapping and reconnecting of these magnetic field lines acts like a cosmic whip, accelerating particles to nearly the speed of light in an instant. This process can unleash a staggering burst of energy across the electromagnetic spectrum, including a brilliant, fleeting flash of radio waves that we detect as a fast radio burst. The timing fits perfectly. These magnetic explosions happen in milliseconds, matching the duration of the signals we observe. The energy scales, while immense, are theoretically possible from such an extreme object. The most compelling evidence arrived in April 2020. A magnetar named SGR-1935+2154, located within our own Milky Way about 30,000 light-years away, entered an active phase. It emitted not just its usual X-ray bursts, but a tremendously powerful radio burst. For the first time, astronomers witnessed a magnetar in our galactic neighborhood producing a fast radio burst like those seen from distant galaxies. This was a smoking gun, a direct observational link that proved magnetars are indeed capable of generating these mysterious signals. Yet, even with this evidence, the mystery is not fully solved. Understanding magnetars is key to demystifying many signals, but their extreme nature means they still operate at the very edge of our comprehension. Not every magnetar outburst produces an FRB, and not every FRB has been traced back to a magnetar. The incredible diversity of fast radio bursts, some repeating erratically and others firing just once, suggests we might be looking at different types of magnetars, or magnetars in different stages of their life, or perhaps even magnetars interacting with surrounding debris or companion stars. The confirmed galactic FRB was also slightly less energetic than its extragalactic cousins, leaving open the question of whether the most distant, most powerful bursts require an even more violent trigger. This leaves the door open for other, even more exotic possibilities to explain the signals that do not quite fit the magnetar model. The existence of these cosmic powerhouses does not close the case. It simply gives us a powerful new suspect, a natural phenomenon so violent and strange that for decades, its predicted effects seemed like science fiction. In the magnetar, we have found a universe that is brilliantly, destructively creative, capable of generating its own profound enigmas without any help from intelligence at all. A magnetar's fury gives us one answer, but the signals themselves often carry another layer of mystery within their very structure. Every extragalactic radio pulse racing toward Earth must travel through a sparse, invisible sea. This is the intergalactic medium, a thin soup of ionized gas and plasma that fills the vast spaces between galaxies. As a burst of radio waves journeys for billions of years, this plasma acts like a cosmic prism. It does not bend light, but it slows it down, and crucially, it slows lower-frequency radio waves slightly more than higher-frequency ones. The result is dispersion. Imagine a crowd of runners starting a marathon together. the faster runners, representing the higher frequencies, gradually pull ahead of the slower ones. By the time they cross the finish line at our telescopes, they arrive staggered. The greater the distance traveled, the more plasma the signal has slogged through, and the more stretched out or dispersed the burst becomes. For astronomers, this smear is not a problem, it is a gift. By measuring precisely how much the signal has been stretched, they can calculate a dispersion measure, a number that serves as a cosmic yardstick. It tells them, in effect, how much stuff the signal has passed through, which correlates strongly with its distance from Earth. This is how we know many fast radio bursts come from galaxies billions of light years away. But what happens when the yardstick gives a reading that makes no sense? This is the conundrum of anomalous dispersion. Some detected signals have dispersion measures that simply do not fit. They might suggest a source impossibly far away, beyond the observable universe, or oddly close, but coming from a direction where our maps show no plausible galaxy. Alternatively, the dispersion might be too clean, or have a strange shape that does not match the smooth distribution of plasma we expect. An anomalous dispersion measure is a red flag, a sign that something is off with our basic assumptions. One possibility is that the signal did not take a direct path. It could have been lensed or scattered by dense, invisible clouds of plasma we have not yet charted, like a voice echoing through a complex canyon, making its origin and travel history difficult to pinpoint. Another, more profound possibility is that our understanding of the plasma distribution in the universe is incomplete. The cosmic web is not a uniform soup. It is a filamentary structure with dense knots and vast voids. A signal passing through an unusually dense or unusually empty region would throw off our standard calculations, using the burst itself to reveal hidden structures in the invisible architecture of the cosmos. Most intriguingly, a handful of signals show almost no dispersion at all, as if they popped into existence right on our cosmic doorstep. These are the most baffling, as they defy the fundamental rule that all long-distance travel leaves a mark. They force scientists to ask, could these be local, from within our own galaxy, but from a source so exotic it mimics an extragalactic burst? Or is there some new physics at play, a propagation effect we have not yet modeled, that can erase the expected fingerprint? Each anomalous signal is more than a mystery, it is a probe. By wrestling with these discordant notes in the data, astronomers are not just looking for the source of the signal, they are using the signal to look at everything it passed through along the way. The universe is using its own most enigmatic whispers to teach us about the darkness between the stars. Every unexplained signal carries a double echo, one in our data and another in our collective imagination. The pursuit of these cosmic whispers is far more than a technical exercise. It is a profound human endeavor that touches the deepest questions of our existence. Each new anomaly triggers a powerful three-part reaction. First comes the scientific rigor, the meticulous process of ruling out every mundane explanation. Then, when a signal survives that initial gauntlet, a wave of public excitement inevitably follows, a thrilling sense that we might be on the verge of a historic discovery. Finally, and most enduringly, comes the philosophical wonder, the quiet awe that these mysteries inspire as we stare into the void. This cycle speaks to something fundamental within us, a need to know if we are alone, and what our own story means in a cosmos of such immense scale and age. This brings us face to face with the Great Silence, a paradox first articulated by the physicist Enrico Fermi. If the universe is so vast and so old, with hundreds of billions of stars in our galaxy alone, each potentially hosting planets, then where is everybody? The sheer statistical probability suggests that other intelligences should have arisen, and perhaps even visited or made their presence known by now. The fact that we have not found definitive proof that we are met with this profound quiet is one of the most puzzling observations in all of science. Yet, the baffling signals we have discussed are not an answer to this silence. They are what keeps the question vibrantly, urgently alive. Each one, whether ultimately traced to a magnetar's starquake or left forever unexplained, represents a possibility. They are constant reminders that our current understanding is incomplete, that the cosmos is capable of phenomena we have not yet catalogued, and that within that vast catalogue of the unknown, other minds could certainly be hiding. These signals actively challenge an anthropocentric view of the universe, the idea that reality must conform to human scales and human timelines. A civilization just 1,000,000 years more advanced than ours would be as incomprehensible to us as our technology would be to a Stone Age ancestor. Their methods of communication, their very perception of reality, might be so different that their signals are all around us, but we lack the conceptual framework to recognize them as anything but natural noise. The signals force us to consider the breathtaking diversity that a universe 13.8 billion years old might produce, not just in terms of life, but in the very laws of physics as expressed in different corners of space. They humble us, they tell us that we are newcomers listening with primitive ears to a conversation that may have been going on for epochs, and in that humility lies a strange kind of hope. The search itself, the act of listening despite the silence, becomes a testament to a uniquely human curiosity. It is our way of reaching out, of saying we are here, and we are wondering if you are too. The value may not be in finding an answer, but in the profound questions we are compelled to ask along the way. That profound silence is not a wall, but a horizon. Our current tools have brought us to the edge of understanding, but a new generation of instruments is poised to carry us across the threshold. The mystery of these cosmic signals is accelerating toward a moment of unprecedented clarity, driven by an international effort of staggering ambition. The Square Kilometer Array, known as the SKA, is not just another telescope. It is a global mega observatory currently under construction across 2 continents, with thousands of dish antennas in South Africa and a forest of low-frequency antennas in Western Australia. When completed, its combined collecting area will span, as the name suggests, approximately 1 square kilometer, making it the most sensitive radio telescope ever built by humanity. Its power is difficult to overstate. The SKA will be so phenomenally sensitive that, in theory, it could detect the equivalent of an airport radar system on a planet orbiting a star tens of light years away. It will scan the sky thousands of times faster than today's best instruments, monitoring vast swaths of the universe in real time. This leap in capability promises to transform the field from one of catching rare, mysterious events to one of routine observation and classification. Instead of puzzling over a few hundred fast radio bursts, the SKA could discover tens of thousands, mapping their origins with pinpoint accuracy across cosmic history. It will listen to millions of stars simultaneously, conducting a continuous, all-sky SETI survey of a scale previously unimaginable. This immense wave of data will not just give us more signals, it will give us better signals, captured with such fidelity that their subtle characteristics, currently lost in the noise, will become crystal clear. We will see the intricate structure within each millisecond burst, potentially revealing the precise mechanisms powering them. The dream is to capture a signal with truly unambiguous characteristics, one that carries a pattern or modulation that cannot be explained by any known astrophysical process. Alongside the SKA, a suite of advanced space-based observatories, like the James Webb Space Telescope and future missions, will provide the crucial visual context. When a strange radio pulse is detected, these powerful eyes can immediately scrutinize the exact galaxy or star system it came from, searching for any accompanying visual anomaly, like the flickering of a Tabby star. This multi-messenger approach, using both ears and eyes on the cosmos, is key to turning anomalies into answers. The coming decade promises not just more data, but a potential paradigm shift. What baffles scientists today may become textbook astrophysics tomorrow, as we move from simply detecting these whispers to truly understanding the colossal engines that produce them. The next great discovery is not a matter of if, but when, and it will be heard through the most powerful ears our species has ever built. The immense power of instruments like the Square Kilometer Array represents one side of the search, but the other side is powered by something far more personal, the shared curiosity of millions. Unraveling cosmic mysteries has never been a solo endeavor reserved for those in white lab coats. Today, the quest to understand the universe's strange whispers is a profoundly democratic one, a collective human effort powered by the screens and spare moments of people around the world. This is the story of citizen science, where the line between professional astronomer and curious observer beautifully blurs. For decades, projects have harnessed the distributed power of home computers, asking volunteers to donate their machines' idle processing time to sift through the mountains of data produced by giant telescopes. The most famous of these was SETI at Home, a program that for over 2 decades turned millions of personal computers into a single, planet-sized supercomputer, analyzing radio signals for the subtle signs of intelligence. While now in a hibernation phase, its legacy is monumental, having processed billions of data units and involving participants from nearly every country on Earth. Its success proved a powerful principle that the computational power needed to find a needle in a cosmic haystack could be gathered not from one expensive facility, but from the collective goodwill of a global community. This model has evolved into even more interactive forms of discovery. Platforms like Zooniverse host a universe of projects where anyone with an internet connection can contribute directly to cutting-edge research. You might be asked to visually scan radio telescope data spectrograms, looking for the unique squiggles that could indicate a fast radio burst, or classify the shapes of distant galaxies to help map the cosmic web that those signals travel through. The human brain possesses an extraordinary, often superior, ability for pattern recognition, especially when faced with complex or anomalous data that might fool a simple algorithm. By distributing tiny slices of this data to thousands of trained eyes, scientists can achieve a level of analysis that would otherwise be impossibly slow or expensive. Every click, every classification becomes a vital data point. Even amateur radio astronomy networks play a crucial role, with hobbyists around the globe monitoring the skies with their own dishes, sometimes catching transient events that professional scopes pointed elsewhere might miss. This vast, decentralized network acts as an early warning system for the cosmos. Beyond the raw data processing, this public engagement fuels something equally vital: sustained interest and understanding. When people participate directly in the search, they develop a personal stake in the outcome. They follow the news of new signals not as passive spectators, but as active contributors. This grassroots passion translates into public support for funding major scientific endeavors. It inspires students to pursue careers in science, and it fosters a culture that values asking big questions. Every person who runs a background program on their laptop or spends a coffee break classifying celestial images becomes part of the largest search party in history. They are not just helping scientists, they are embodying the very spirit of exploration. This collective endeavor demonstrates a profound truth about the signals that baffle us. The quest to understand them is not driven by a single institution, but by a shared, species-wide yearning to know our place in the cosmos. It is a reminder that the most powerful instrument in this search may not be a telescope, but the connected human mind, tirelessly scanning the static for a whisper of meaning. Our journey through cosmic whispers has brought us face to face with a gallery of enigmas, each a unique fingerprint left by the universe. Let us assemble this mental catalogue of the 20 most baffling signals, a testament to the strange and varied language of deep space. We began with the legendary WOW signal, a perfect 72-second shout on the hydrogen line that has never been repeated, the ghost that started it all. From there, we witnessed the raw violence of the Lorimer burst, the first recognized fast radio burst, a millisecond flash brighter than the sun for months. We met the repeaters like FRB 121102, firing sporadically from a turbulent dwarf galaxy, proving some cosmic engines survived their own detonations. The silent, patient heartbeat of the Galactic Center radio transient pulsed every 77 minutes from our own galaxy's core, a slow metronome of unknown origin. We encountered tantalizing false alarms that taught us crucial lessons, from the Perytons of a microwave oven to the human-made mirage of BLC-1 near Proxima Centauri, and the citizen science candidate SHB-02+14 that faded into silence. We saw how optical mysteries like Tabby's star prompted urgent radio listens that found nothing, and how a sun-like star, HD 164595, briefly sparked hope before being traced to our own satellites. The discovery of pulsars themselves, initially labeled LGM for little green men, showed how a solved mystery can open entirely new fields of science. We explored the strange realm of signals with mysterious periodicities, repeating on schedules of days or weeks that hint at orbital dances or wobbling magnetic fields. The search broadened into the hunt for technosignatures, from laser pulses to infrared glows of theoretical megastructures, acknowledging we might be listening on the wrong channels. We found a likely culprit in the magnetar, a neutron star with magnetic fury capable of generating immense bursts, yet this explanation cannot yet account for every signal's peculiarities. Some bursts arrive with anomalous dispersion measures, their fingerprints smudged by unseen plasma clouds or hinting at travel paths we cannot map. Underpinning it all is the philosophical weight of the great silence, the profound quiet that makes each unexplained whisper all the more significant. This catalogue is not merely a list, it is a spectrum of mystery. It contains one-off cataclysms and scheduled repeaters, local oddities and extragalactic sirens, radio shouts and their silent optical counterparts. Each entry, whether eventually explained or forever enigmatic, represents a frontier. They are pieces of a vast cosmic code, a language of energy and time that we are only beginning to parse. The sheer diversity tells us something essential. The universe is not just stranger than we imagine, it is more creatively mysterious, employing a multitude of bizarre mechanisms just to get our attention. This collection is our starting point, a map of the known unknowns, and every point on it is a destination for the next generation of explorers armed with tools like the square kilometer array. From a solitary red pen exclamation to a relentless cosmic chorus, these 20 signals form a single, compelling portrait. They reveal a universe that is not serene and silent, but dynamically creative and often shockingly violent. Each unexplained ping, burst, and heartbeat is a testament to nature's boundless imagination, operating on scales and with energies that stretch our comprehension to its limits. These phenomena baffle scientists, but this bafflement is not a sign of failure. It is the essential fuel of discovery. Every anomaly is a beacon, its strange light pointing toward entire new chapters of physics waiting to be written, toward celestial objects and interactions we have not yet dreamed of cataloging. They are guideposts in the dark, and some may one day lead us to the most profound discovery of all. A sign that in all this magnificent chaos, we are not the only minds wondering about the night. The search is accelerating, powered by a new generation of telescopes with unprecedented sensitivity, by algorithms that can sift noise from signal in real time, and by that most human of engines, a relentless, innate curiosity about our place in the grand scheme. So when you next look up at the seemingly silent stars, understand this: the quiet is an illusion. The cosmos is a vibrant, crackling arena of conversation, written in the language of energy and time. It is broadcasting its secrets in furious millisecond shouts and patient, repeating rhythms. We have only just begun to tune our ears to the correct frequency. The greatest messages may still be waiting in the static, and it is entirely up to us to learn how to listen. If this journey to the very edge of our understanding captivated you, we would love to hear your thoughts. Which of these cosmic whispers intrigues or puzzles you the most? Share your perspective in the comments below, and subscribe to join us as we continue exploring the universe's greatest, most beautiful mysteries.